It's March 25th, less than 2 months until Arada. By that time I realized that I couldn't just go with the ORCA one, even though it had such amazing results. The machine itself had many flaws which had to be corrected. First, there was no user interface. If you wanted to change anything in the code, you would have to manually move with your laptop from your workspace all the way to the ORCA one, plug in the cable and then hit upload. And I just couldn't get my head around the fact that if any of those AC cables would touch each other, then we would all burn the magical spark. Not only that, but the enclosure's door also had a slight play, so inevitably some heat would be lost to the outside. Now, my cultures have grown exceptionally well even with all these flaws, but there's a saying that if you can't make it better, then do it. With all of that in mind, I really just started thinking what would be safer and easier to use for anyone that owns an ORCA. So first, I changed pretty much anything that was on AC to DC, added a brand new power supply. The aquarium pump was now a 12 volts diaphragm pump. The LED strip and the light bulb will also be replaced by a 12 volt IP68 RGBW LED strip, which I could also place directly in the water. And to support all these amazing changes, I decided to make a much more rigid structure, which was now made out of aluminium. And not only that, but it was also time to centralize all the wirings. Let's face it, it's extremely unpractical to have to go to your machine every single time you want to upload a new firmware. So, let me introduce you the Raspberry Pi. As a quick disclaimer, this is Raspberry Pi 2, all the other Raspberry Pis I have are either burnt or in one of the ORCAs. And by replacing the Arduino with one of these, a whole new world of possibilities opened to me, and that including adding a real camera. Because yes, the ORCA one did have a camera, but it was a USB one, and you were supposed to add your laptop on top of the shelf you were sitting on and watch it from there. And to be honest, it doesn't sound good at all to have your laptop stuck on your ORCA. And say you have multiple ORCAs, then what are you going to do? Then buy multiple laptops, one for each ORCA? What? And the camera that I added is one that connects directly to the Raspberry Pi. What this means is that if you connect it to the internet, then you're going to have access to it from anywhere in the world. And not only that, but you can also run artificial intelligence models on it using TensorFlow or whatever custom model that you train yourself. And this is a huge improvement from the Arduino, because imagine an AI just taking care of your entire cultures. Say you have multiple bioreactors, all of them sitting in a huge room, and why would you have to bother to check each and every one of them every single day when you can have a program, a software telling you if they have enough light, if they need more nutrients, if they need more carbon dioxide, and all of this is just so amazing. Now, getting over the pink and rainbows that using Raspberry Pi was, I also kind of shot myself in the foot by using it, and we'll get on that later. Other than the Raspberry Pi, there were quite a few new parts. Before all, finally, a touchscreen with a friendly user interface, which also worked because the ORCA one also had a screen, not a touchscreen, which now allowed us to control the machine from outside the Python IDE, a DHT22 for real-time temperature and humidity detection in a room, where I also shot myself in the foot again. Two DS18B20s, which were much cheaper than their DHT counterpart and also much more reliable. A brand new industrial pH sensor which can stay submerged for up to 6 months continuously. Just that easy, no maintenance. And for the movement components, we have 4 end-stop modules, 1 Hall sensor, 3 stepper motors, and 3 drivers for them as well. My wish for a fully enclosed photobioreactor led me to designing a machine which would rise its growing cell up and then retract it while also sealing the chamber. This is why I mentioned adding 3 stepper motors and multiple position sensors to determine where the cell is. The reactor has 2 main moving parts. 1, the locker, and 2, the platform. Brings the vase up and the locker prevents it from spilling any water. This is because even though the stepper motors are really slow, maybe because of the huge reduction ratio gearboxes, with vibrations comes the risk of water getting out of the glass, which is extremely bad when you're working with electronic components. The locker makes sure this never happens, and it also serves an auxiliary function to guide all the cables and tubes inside the cell. For the ORCA one, I had to go every 3 days and manually insert my nutrients mixture into the culture, which was heavily unpractical. What if I went outside the city? So, for the ORCA 2, I decided to add 4 different pumps. 1 for the nutrients, 2 for the special in and out, in case you want to extract the sample of your culture and analyze it, or you want to insert some other solution into the water other than the nutrients that you are already giving. And the last pump was reserved for the bubbling and also the heating. We'll talk about that later. And the last addition to the consumables was a 4 liters canister of CO2, which you could easily refill using baking soda and citric acid. What does this mean is that you don't have to spend any money on those CO2 canisters and you can manually refill them for pretty cheap at home with zero experience. I mentioned heating and bubbling were happening at the same time. Well, this is because on the previous ORCA I had a dedicated aquarium heater which was consuming about 10 to 25 watts to do its job, which is at least 10 times more than what the ORCA 2 takes for the same job. On the air puffs to getting in the water, there is an annealed PLA station in which lays a DS18B20 sensor and a resistor which constantly heats up according to the values which the sensor is picking up. By heating the resistor to the values that we want, which is being read by the sensor, we can achieve the same results as the resistive aquarium heater, and all of that for roughly 1 or 2 watts. The result is a smaller electricity bill, but as a consequence, we'll have to wait longer until the water reaches our desired temperature. PLA is one of the worst materials to work with in warm environments. So for the next machine, I decided to make most of my parts using PETG. My initial thought was to 3D print the entire PBR, which was heavily impractical and really expensive. So with that in mind, I discovered aluminum profiles exist and ordered multiple 40x40 extrusions according to the 3D models that I made, which was kind of a huge overkill in terms of strength, as I could have easily done everything with only 20x20 ones. As for the walls, there was no way I could 3D print 30x40 centimeter objects on my Prusa, so I purchased some off-the-shelf PVC boards and headed to my uncle's that he could help me with his professional tools to cut them all for me, where he did an amazing job considering how fast he did them all. Even with the walls and structure ready to rock, there was still one question: how are you going to fix those motors and linear rails on the bottom of the reactor? Which brings me to polycarbonate. Also known as one of the strongest 3D printing materials, it is perhaps the king of DIY 3D printing. So I decided to give it a shot on my Prusa and print the most critical and stressed parts with it. Ideas are all good and all, but how are you going to print it? Polycarbonate requires an enclosure, otherwise it's going to warp like crazy. And the original enclosure for the Mark III costs roughly 370 euros, and that without any of the add-ons that Prusa offers. So I decided to use my brain and obtain a more affordable solution. Introducing fancy aluminum foil. Just wrap it around the printer, leave a gap for an air filter, and also want to be able to reach the power supply and its shutdown button, and a camera on top. And voila, just like that, for less than 100 euros, I would say even less than 80 euros, you've got yourself a kind of functional enclosure, which will print polycarbonate just fine with only a tiny bit of warping. The rest of the 3D printed parts were all made with PETG, except for the heating chamber, which allowed me to remove the enclosure and finally be able to breathe well in my room, as polycarbonate is known to be toxic due to the presence of bisphenol A or BPA. With PLA and PETG, you can easily stay in the same room with the printer. And as a fun fact, my longest print, the Sail platform, took 4 days to print. This means the Prusa has been working continuously for more than 96 hours. Aside from the printer being incredibly reliable, it was also super silent, as since I had nowhere else to place it, I slept in the same room as with the printer while it was on. And honestly, I didn't even notice it. Obviously, nobody should be spending so much time in the same room as with the printer you're using, but because of space and financial constraints, I had no other option. If the ORCA 1 was completed relatively easily since it costed roughly 600 euros for all the materials and components, the ORCA 2 was obviously a much bigger challenge for my family. To achieve this project, we did have 2000 euros sent to our high school from some amazing people that decided to sponsor my projects, but due to a couple of reasons we were not able to access them. Having made such huge mistakes, it meant we had to rely on our own funds. Here, I'm incredibly thankful to my family for supporting me in everything that I've done, because the funding of ORCA 2 was no easy task. There are two major mistakes that I made during the ORCA 2 development. Firstly, the locking mechanism is kind of non-functional due to the fact that by design it doesn't have any support to keep it perpendicular to the ground. And whenever you try to lift it, you have to manually hold it by hand in a certain position so that it lifts up. Otherwise, it won't work. And secondly, just 2 weeks before the contest, everything was done. The motors, the Raspberry Pi, the sensors were attached to the main board. And what I did was to attach the 3.3 volt step-down modules to the system. So what step-down modules essentially do is that you input some voltage and they're going to output a certain fixed voltage which is rated by the manufacturer. Say you input 12 volts, if you have a 3.3 volts step-down module, then that is going to output 3.3 volts. Now, of course, any step-down module has some input pads and some output pads. And the way you should wire it is that whatever comes from your power supply should come to the input, and whatever goes to your electronic sensors, whatever, is going to be on the output. Well, what I did was to inverse the channels, and instead of connecting the power supply to the input, I connected it to the output, and the sensors, instead of being to the output, they were in the input. And that was a devastating mistake. As I mentioned previously, by using the Raspberry Pi instead of the Arduino, I kind of shot myself in the foot, because to replace a Raspberry Pi would cost you around $100 to $200, depending on which model you got. Whereas for an Arduino, you can easily find one for $10 to $20 or euros. They're really cheap. And by getting in 12 volts from 7 different channels, 7 different pins on the Raspberry Pi, the board was completely done. I really tried to boot it again to see if there was any way. I didn't really know what happened in the beginning. I thought that it was something beyond my understanding, and in that moment I lost almost 200 euros in less than a split of a second. So the moment I saw the smoke, even though I was really fast to disconnect everything, the moment you see smoke, it's already too late to do anything to it. And even though I felt really bad about what I just did, I knew I had one more chance. So my electronics teacher, he's not actually from high school, he's from somewhere else. He was kind enough to send me a Raspberry Pi 2 from his inventory. I looked on the electronics, I looked on everything I could to see what was the problem, but the only issue that I spotted at first glance was the DHT sensor being wired the opposite. So the ground was to the VCC and the VCC was to ground, and that alone I don't think was capable of sparking and getting all the smoke out. I did fix that problem, yes, and I started checking again to see if there were any problems, and I didn't see any problems. Like, I thought it was from the sensors, not from the step-down modules. I thought that they're from Pololu, and Pololu is supposed to be one of the best step-down modules manufacturers, so it can't be because of that. And then foolishly I connected everything again. But the only different thing that I made this time was that on the board there are 3 inputs, so the 12 volts, 5 volts and 3.3 volts line. And I disconnected the 3.3 volts line because that was the most recent one I added, and before that everything was working well, and it was working really fine. I still had the power supply on, I had the Raspberry Pi 2 on, and then thinking I solved the problem, I connected the 3.3 volts line again, and it just blanked. The screen was black and there was no more connection. Also, both of the power LEDs, which are supposed to blink on any Raspberry Pi, were not off. In that moment, I had a thought of quitting, but it's not about that. And to my surprise, my parents talked to each other, and they told me, here's 200 euros more, spend them on whatever you like. I didn't really know how to respond to that, and with that being said, I also told my electronics teacher what just happened, and he also told me he would give me a Raspberry Pi 2, and I was just amazed by how lucky I am to have such amazing people around me. But even with all of this, I realized that if I wouldn't find the root cause of all of these problems, then I would end up burning all of the brand new Raspberry Pis as well. And I had like 24 hours to think and just tear down all the wirings and see what was the problem. And as complex as I thought it would be, it was just very simple. As I said, the issue was not a quantum physics problem, but rather just a flipped wiring. And after I resoldered everything, I tested the circuit again. It did not burn. The sensors were also reading. By that time, also the 4B and the 3A Plus came, but I wasn't willing to take the risk to burn another 4th version again. Now, with that being said, I just want to thank my family and my electronics teacher again for all the support they gave me, because burning 2 pies and then being given 3 more to experiment with is, I believe, beyond being human. Because there was just 1 week left until the robotics championship and I still had to do some minor adjustments to the code, I did not take any videos of it while working. What I did was to take about half of the chlorella vulgaris that I had in my previous bioreactor and insert it in the ORCA 2. And just like that, it worked. And in those 5 to 6 days of staying in the PBR, again, it was a semi-mature culture, they managed to grow so much that I was able to extract exactly 2 samples. These 2 samples are from the ORCA 2 and the only labeled one is from the ORCA 1. Can you tell the difference? I don't think so. Overall, both of the ORCAs have done an amazing job at growing these cultures, but as far as I see, the ORCA 2 seems to have grown them to a higher maturity state. As you've seen, it's just as if time was on our side. Everything was finished exactly in time. I designed, ordered, 3D printed, assembled, and programmed everything. And all of this was just within the 25th of March and the 19th of April. It's kind of amazing what one can do just with his free time and whatever is left during high school. And I'm extremely thankful for everyone who has supported me so far, because without them, I wouldn't be here and today we would have no story to talk about. What happens next? Will there be an ORCA 3? Will there be an Abrams 2 or perhaps a Candy A2C? I can't say for sure, but what I do know is that any project that I take should be challenging. But perhaps most importantly, it should define the future.